Hello, this time we're going to look at AC power in capacitors and inductors. I will start by having a look in the simulator. Now this is what happens with resistors. The voltage, that's the purple line here, and the current, that's the blue dotted line here, are in phase, which means if we multiply them together, we get this power, which is always positive and oscillates at twice the frequency of our voltage source. Now, what happens if we swap the resistor with a capacitor? Now you'll see that the voltage across the capacitor and the current through the capacitor are now 90 degrees out of phase. When the current is at its maximum value, the voltage across the capacitor is 0. When the voltage is at its maximum value, the current through the capacitor is 0. And if we multiply these two together, then we get this. It's an oscillating waveform. Again, it's oscillating at twice the frequency of our voltage source, but now it has an average value of 0. We have both positive powers and negative powers associated with this component. What about inductors? Inductors give us the same kind of situation. The voltage and the current are 90 degrees out of phase, so if we multiply them together to work out an instantaneous power associated with the inductor, we get an oscillation which is going both positive and negative. There are times when the voltage is positive and the current is negative, and that gives us a negative power. Now this is exactly what we should have expected. If we take the fundamental equation that defines the behavior of inductors, the voltage is the inductance times the rate of change of current, and substitute in a current which is oscillating, I0 sine omega t, that produces a voltage which is also oscillating, but 90 degrees out of phase. If the current is a sine wave, the voltage is a cosine wave. And if we do the same thing with the fundamental equation for a capacitor, the current is the capacitance times the rate of change of the voltage. Substitute in a voltage, which is oscillating sinusoidally, we get a current which is behaving like a cosine wave, 90 degrees out of phase with the sine wave. And this gives us curves like this. The current and the voltage are 90 degrees out of phase. Sometimes the current and the voltage are both positive, so the power will be positive. Sometimes the current and the voltage are both negative, so the power will be positive. But at other times, the current is negative when the voltage is positive, and you end up with a negative power. Or the voltage might be negative when the current is positive, like here, and again you end up with a negative power. So we're getting both positive and negative powers associated with this capacitor component. What does this mean? Well, you have to remember that a positive power, the way we've been describing positive powers, is a power which is being lost from the circuit, energy being dissipated. Whereas a negative power being lost corresponds to a power being input into the circuit, like from a voltage source or something like that. So if we have a power which is both oscillating negative and positive, that suggests we have a component which some of the time is extracting energy from the circuit and the rest of the time is pushing energy back into the circuit. And that's exactly what is happening with this capacitor. The electric field in the capacitor itself, the electric field between the plates, is charging up. And as it charges up, it extracts energy from the circuit and stores it in the electric field. But then, as the voltage across the capacitor returns to 0, the electric field in the capacitor collapses, and the energy that was stored in it is pushed back into the circuit. Ideal capacitors dissipate no power. They don't lose any energy. all they do is that they alternately store energy in their electric field and then push that energy back into the circuit, and then store energy in the electric field in the other direction, and then push that energy back into the circuit, and then store energy as they charge up, and then push that energy back, and then store energy as they charge up in the negative direction, and then push that energy back, and so on. And they're continually extracting and then returning energy to the circuit. So the average value of the power being dissipated by a capacitor is 0. But we can work out a maximum instantaneous power associated with the capacitor. And we can do that by going back to our formula that always works. The instantaneous power is the instantaneous voltage across a component times the instantaneous current flowing through the component. If we have a voltage across our capacitor, which is given by V0 sine omega t, then our current is going to be 90 degrees out of phase with it, and we could write it as I0 cosine omega t. So that would give me a power as a function of time, which is V0 times I0 times sine omega t times cosine omega t. And using another one of those useful standard trigonometrical identities, I can write that as V0 I0 over 2 times sine of 2 omega t. The average value of that is 0, but the maximum value occurs when sine of 2 omega t equals 1. The maximum instantaneous power is therefore the voltage amplitude times the current amplitude divided by 2. It's very similar to the formula that we had for the average power being dissipated by a resistor. But this time, this is the maximum power that is being either stored or returned to the circuit from the capacitor. We could go through the same thing for inductors, and we would get exactly the same answer. The instantaneous power is V0 I0 times sine 2 omega t over 2. Its average value is 0. Its maximum value is the amplitude of the voltage times the amplitude of the current divided by 2. And we'll come back to both of those formulas later. Next time, we'll have a look at what happens in a real passive network, and not just an ideal capacitor, an ideal inductor, or an ideal resistor.